Hello everyone out there in physics land. This is your friendly heavy physics teacher one more time with a lesson, this time on natural resonance. And because the basic concepts of natural resonance is fundamental to both my physics classes, this is going to be a lesson for both the college physics and the Regents Physics class rolled into one. I will differentiate the instruction when we do our online sessions together, okay? So for the college physics class, this is Unit 10, Lesson 9. It's the last lesson in that particular unit. And it's the second to last lesson in the unit. We have one more lesson after this on the Doppler effect. And then for the Regents Physics class, this is Unit 11, Lesson 6, and this is definitely your last lesson in this unit, okay? So we're going to be talking about natural resonance. Okay, so what do we mean by natural resonance? All right, we talked a little bit about resonance in some other areas of this unit, but now we're going to talk about it specifically for this. All right, resonance represents an amplification of a wave. It can be any kind of wave. I'm going to deal almost exclusively with sound for this. Okay, so here I have a particular empty soda bottle. And if I create a disturbance across the top of the soda bottle, we get the classic. I hope you can all hear that. And you have to do it at kind of just the right speed in order to make it happen. Okay. Now, what happens if I change the amount of air that's contained within this bottle? Well, I just happen to have with me a bottle with, as you can see, I've got water in it. Okay. And now if you listen, okay, so I've got two different frequencies being produced by the same bottle, but this bottle has water in it, and so it's only got this much space for the air to vibrate. Okay, take a different bottle. All right, as you can see, it's a little larger than the other ones. Okay. All right, so much lower note, and then if we go to another extreme, all right, all right, so we've got an even deeper bottle, all right, even deeper tone. All of this is happening due to resonance. Okay, at its basic definition, resonance is the amplification of wave. Amplification means the increase in amplitude, right? So the amplification of a wave by applying a force to the wave at the same frequency that the wave is vibrating at, okay? So we can think of that as pushing a child on a swing or musical instruments, okay? So this is the basic definition of resonance. Making the amplitude larger when you apply a force at the same frequency as the wave that's being made. Okay, so natural resonance is when you actually reflect a wave back on itself. And if the distance of the reflection is just the right distance, then that creates a standing wave. And that standing wave pattern, the constructive interference parts of that standing wave pattern create the resonance that we hear. All right? So here's the way this works physically. And I'm going to do a kind of stop motion thing that I experimented with here, and I hope it works here for us. Okay, this is a picture of a tuning fork in front of a tube of some sort, okay? Now, this is exactly the same thing as I did starting the discussion, okay? If we were to do this like so, here's my soda bottle, and as I breathe across the top, that's creating a disturbance which creates pressure waves, okay? So the tuning fork is going to create a pressure wave that is going to get pushed down into the tube and then come back out, all right? Because it's reflecting off of the end of the tube there, all right? So here's the way this works, all right? As the tuning fork vibrates, it's going to press out on the air molecules, creating a high pressure area that then eventually becomes a low pressure. Well, let me start drawing. Okay, so what I was drawing there was my tuning fork vibrating in and out, and it's creating a variation in the pressure of the air, which is the sound wave that we hear. Okay, and so it began with the tines kind of close together, so we had a high pressure. That high pressure starts to decrease as these tines go out. Well, that information is traveling down the tube. Okay, and so it travels down the tube. The pressure becomes low at this end as that pressure wave gets to here. Now, because this is a rigid boundary at the end, the reflection also flips the amplitude. So the reflected wave in blue here coming back has the opposite amplitude. And when it gets to here, that's back when this is a compression, but this is also high pressure. So this is reinforcing this right here. That's why this is resonance. So that pressure wave, the information in that pressure wave goes down, gets reflected, and by the time that information gets back, it's the same thing happening here that went down and back in the first place. Okay? And so this is a standing wave. It happens to be 1/4 of a wavelength. All right? The first part of the wave goes out, it gets reflected back. All right? And by the time it gets back here, the next half of the wave is about to begin for this. Okay? The next half of the wave is about to begin. This is going to vibrate in and out. All right? Now, this can only happen if the frequency of this vibration creates a wavelength that fits into this space. And all we need is 1/4 of that wavelength if it's a closed end over here. Now, if it were open end, it would have to go out and reflect off of a soft boundary so that it comes back on the same path and reinforces it. So an open pipe resonator needs a half wavelength. The length needs to be a half of the wavelength that will resonate in it. Okay? Okay, back to my bottles again. All right. So we've got an empty bottle, half full bottle. All right. Let's think about this. This distance down is 1/4 of the wavelength that will resonate in the bottle. All right. That will resonate from the bottle. And so the frequency that we hear, it corresponds to the wavelength that is getting reflected back up in here. All right. This frequency is higher because the wavelength is shorter. The speed of the wave, the speed of sound is the same for both bottles. Speed of sound is the same for both bottles. So longer wavelength, lower frequency for that same speed. Shorter wavelength means you need a higher frequency to compensate for that, the same speed for both of them. Okay. Yeah, if I had a whole bunch of them, I could tune them and I could play an octave. Okay, and all would depend on how far, how deep into this that I wanted to go. Now, there's always only one frequency that will a low frequency that will naturally resonate in a given space. You can create harmonics. College physics guys, remember we talked about harmonics? You can create harmonics if a shorter version of that wavelength could create a standing wave in the same space. College physics guys, we'll get into that. We'll revisit harmonics. Regents Physics guys, the thing you need to know is that the length here represents the wavelength that can resonate in this space. So we have two types of resonating chambers in nature, all right? We have what's called the closed pipe resonator, and the closed pipe resonator will resonate when the length of the resonating chamber, the length of the tube, if you will, the length of the pipe, is equivalent to 1/4 of the wavelength that will resonate in it. Now remember, that wavelength corresponds to a particular frequency for the speed of sound at that temperature. Okay? So you only get one fundamental wave resonating at a particular length if it's just 1/4 of it. Now remember, it has to be a closed pipe for it to be 1/4. If it's an open pipe, like a guitar string, like a flute, like a clarinet, like a trombone, like a trumpet, French horn, any woodwind, any brass, any stringed instrument obeys this rule down here. These are for whistles. These are for soda bottles. Okay, this one right here. These are for anything that vibrate in a half wavelength mode for their fundamental vibration mode. Guitar strings, half wavelength. Okay, piano strings, half wavelength. All right. So if it has a half wavelength vibration mode in the length of the string, in the length of the tube, in the length of the flute, in the length of whatever it happens to be, as long as it has that half wavelength vibration mode, that's creating a standing wave that's going to resonate in it. Okay? So if it's an open pipe resonator, half wavelength, closed pipe resonator, 1/4 wavelength. Okay? Please be on the lookout for the worksheet on resonance. It's just on resonance, so I'll be sending that out. If you haven't already received it, make sure you contact me. And then I will be sending out an answer key shortly following that so that you can see how to do basic resonance problems. All right? Thank you for listening. This has been your friendly heavy physics teacher one more time. It looks like for my kids, I probably will not be seeing you until May 18th at the earliest. Yeah, we just got that announcement yesterday. Have fun, and I will see you in the future. Bye-bye.